one is the lowest frequency mode. I'm looking at ratios relative to it, so that ratio is 1. And that minus sign means that the head is depressed as we're looking at it. If we looked at it half a cycle later, it would be a plus sign, and it would oscillate back and forth. And I'll show you an animation of it so it'll be clear. And then this is the second mode here, and it's 1.59 times, the frequency is 1.59 the frequency of the fundamental mode. And then the next one, 2.14, then 2.30, and you can see that these are not harmonic. Okay, the drum does not give a definite pitch. You can tell if you tune it, if you make the tension higher, it sounds higher, but it's not a note. It's sort of more of a thud. Okay, so now we can see some animations. These were done by Daniel Russell, who I think is at Penn State. Is he here by any chance? I know he's a member of AAPT because I looked him up. And that's the first mode, and you can. And here's the second mode. And this the first one looks and is referred to often as a. I'm pointing with my left hand instead of pointing. This is a monopole. This is a dipole. There's a quadrupole. And then 0, 2, I don't know what you call that, but I'm sure we can find the name for it. And this just shows that one is called a monopole and one is called a dipole. Mode. And then cycles, it's going to go back down. There it is, 82.2. That's the 0, 1 mode. You can recognize it. That's the first mode. And the second mode is this one. You can see that's the dipole. And I think it becomes clear as you look at it. And again, that's Daniel Russell. But this is not a typical drum, obviously. A typical drum has more to it than just a drum head. And so, for example, if we go to the kettle drum, which we talked about before, the kettle drum, first of all, has not only a drum head, but it has a kettle. The kettle's usually made of copper, but it can be made of fiberglass. There are fiberglass kettles. And I don't know how much the sound varies. I'm sure it varies some, but I don't think it's a tremendously large effect. There's the kettle, there's air inside the kettle, and there's a pedal, and you can hit a note on a kettle drum and adjust the pedal, and it will go, or, you know, or the other way. I'm not a singer. All right, now if you look at the frequency spectrum, and I should say where it's hit, the standard place to hit a kettle drum, if you watch a kettle drum player, you'll see they don't hit it in the center. They hit it closer to the rim. It's about a quarter of the way, roughly, from the rim to the center. And that excites certain modes. And in particular, it excites the 1-1 mode, the 2-1 mode, the 3-1 mode, the 4-1 mode. This is a mode with 1 nodal diameter, 2 nodal diameters, 3 nodal diameters, 4 nodal, and 5 nodal diameters, okay? That's what gets excited. Mainly, the 0-1 mode, the monopole, is excited, but if you look at it a second later, that one's gone. And all these other ones, the 1-1, 2-1, 3-1, 4-1, and 5-1, still remain. And so they give the sound, basically. There's actually a missing fundamental there that the ear the brain sort of makes up for. Microseconds, 60 microseconds, and 300 microseconds. So this is like dropping a pebble into water and watching the waves propagate outward. Here they're only up to about here. After 60 microseconds, they just barely are getting to this edge, and the distance between this point and the edge is about 1/10 of a meter. And if you calculate the speed over 60 microseconds, that comes out to be a little under 1,700, under 1,700 meters per second. Now, more generally, if you can categorize the simple hit in terms of 3 time regimes. The first one is less than a millisecond, rapid wave propagation. That's what we're seeing here. But then there is a buildup of peaks, some of which I think is starting to become apparent here, and a buildup basically of the standing waves, and then an after sound. And each of these is in a different frequency range. Symbols are extremely complex, very nonlinear. if you strike a cymbal, do not try this at home. This is at 1,000 frames per second, so that's about a factor of 40. So what we're seeing here takes place in about a half of a second, actually, but we're seeing it over 20 seconds. You get something like that, but now you don't have to strike it to excite it. You can excite it by, similar to a drumhead, by just using an audio signal. And if you do that here, listen for the beats. That's extraordinary, right? Really, that's called a shimmer. You know, shimmer is usually optical, but that's an audio shimmer. It turns out that cymbals actually exhibit chaotic behavior. I did not know this when I was invited to give this talk. You can get phase plots as a function of the amplitude coming from that speaker. If you increase the amplitude, the phase plots, I won't go into the details because I'm running late, they start to develop bends and ultimately look rather chaotic. This doesn't look this way if the colors are right. It looks more densely packed with stuff. Initially, before you get into the chaotic regime, you have a small number of frequencies, but as you approach chaos, the number of frequencies increases and it becomes dense, I think theoretically infinitely dense as that happens. And then there's a spectrogram which shows the same thing. I did want to say just one thing about the drumstick. And I also want to show that solo. But you can do force versus time experiments. And this one is kind of interesting because it shows a dip over here for the force versus time. If you have a lower tension, it shows a dip at the same exact place. And for a lower tension yet, the dip is at the same exact place. It has nothing to do with the tension, and it has nothing to do with the drumhead. It has to do with the drumstick. Do you remember when I hit the drumsticks together and I said they vibrate? It's vibrating. This drumstick is vibrating. And this fellow, Andreas Wagner, did these experiments. They're really nice for his master's thesis in Sweden in 2005. If you look at the tip's acceleration, you get all sorts of wiggles. He did a Fourier analysis of it and studied the vibrations of the sticks separately, etc. All right, so here's the summary. Talked about waves, vibrational modes, normal modes, time series, spectral graphs, decay times, dipole and multiple radiators, the route to chaos, classical mechanics, energy transformations. By the way, all the energy that goes into smacking the drums, just like all the energy that went into your saxophone and the clarinet, it all ends up ultimately as internal energy of everything around you. It's a thermodynamics problem, and the entropy goes up when that goes on. Okay, I just thought I had to say that. So this is applied physics of interest to students. I strongly recommend you try to look into some of this. This will go by fast, but I can send this list to anybody who wishes. There'll be a list at the end. Now here's the drum solo, not this man. This man's a piano player. But this is by Steve Gadd. And it lasts about a minute, and I hope you like it.